Inserts of Zeta 3, Mathalysis World version. If you guys do not know about Zeta function, let me just give a very short introduction. Zeta function is actually defined by an infinite series, right? So zeta of n would something like 1 by 1 to the power n plus 1 by 2 to the power n plus 1 by 3 to the power n plus 1 by 4 to the power n, and goes on up to infinity, right? And whenever n is greater than 1, this actually converges, right, this series. But like even for, let's say, one less than 1, like we can actually use analytic continuation and find the values. And over here, like till now, we already know values for, let's say, zeta of 2, which is pi square by 6, zeta of 4, which is pi to the power 4 by 90, zeta of 6, which is pi to the power 6 by 945, zeta of 8, which is pi to the power 8 by 9450, and all the even powers are known, right? But the thing is, like, for this zeta 3, zeta 5, zeta 7, we definitely know like their decimal value using computers, right? But like their exact value in terms of known constants is still an unsolved problem. We don't even know if like they have a value in terms of the constants we already know, like let's say pi, or like let's say E, or Euler-Mastroianni constant, or Glaser-Gillen constant, or such things, like in terms of the constant that we already know. Yeah. So yeah, so this is actually a still unsolved problem, and actually there's a whole book dedicated to like finding value of zeta 3. There's a book called In Pursuit of Zeta 3 by Paul Nahin, right? And yeah, this video is actually inspired from him, right? And yeah, also like the ideas here are just from my own fantasy and like need not be accurate or useful whatsoever. Just enjoy or skip as you want. Okay. Yeah. So let's see. Let's go into the problem now. I already described what zeta function is and what we are trying to do today, right? So okay. So I do have an idea, slight idea about why. I mean, how we might be able to find it. So I'm gonna describe that now. Okay. First of all, let me tell you about the reflection formula of zeta function. Reflection formula of zeta function. Which is also called the functional equation of zeta function, right? Which is as follows. This says that zeta of s is equals to 2 to the power s pi to the power s minus 1 sine of pi s over 2, right? And gamma of 1 minus s, sorry, and then zeta of 1 minus s, right? Okay, now from here, like this is like mainly used to find zeta of negative values based on the zeta of positive values, right? We use it for that purpose, but it can be used for more than that. Um, okay, let me just substitute s as negative s, and then zeta of negative s will be equals to the power minus s pi to the power minus s minus 1 sine of negative pi s by 2, and then gamma of 1 plus s zeta of 1 plus s, right? Now we know that sine is odd function, so we can take that negative sign outside. And also, okay, there's actually a formula for zeta of negative n, right? And that is negative Bernoulli n plus 1 by n plus 1, where b sub n stands for nth Bernoulli number, right? I guess you guys know what Bernoulli number, like they come in the like sum of like n natural numbers to the power k, right? You can actually find a video in my channel about that. Okay, so using this thing, we now get negative b s plus 1 s plus 1 is equals to the power minus s pi to the power minus s minus 1, and now this gives us a minus sign, sine of pi s by 2 gamma of 1 plus s, and then zeta of 1 plus s, right? Okay, so now if we try to isolate zeta of 1 plus s, okay, this sign cancels out. Now if I try to isolate zeta of 1 plus s, what I get is Bernoulli sub s plus 1, 2 to the power s, pi to the power s plus 1 divided by sine of pi s by 2, gamma of 1 plus s, and then just s plus 1, right? Okay, now this actually gives us like a direct formula for zeta of 1 plus s, right? And now you might be so hopeful that now I can find average zeta value because I actually have an explicit formula for zeta value in terms of Bernoulli number, right? Yeah, but keep that excitement for now because that won't really be the case. Here's a twist. Okay, so now if you will, let's say, want to find zeta of 2, so what you will do is you will substitute s equals to 1, and that will give me that will give you zeta of 2 is equals to b sub 2, 2 to the power 1, pi to the power 2 by sine of s as 1, so pi over 2 gamma of 2 times 2, right? Now Bernoulli sub 2 is 1 over 6, so 1 over 6 times 2 times pi square by 1 times 1 times 2, 2 to cancels out, you get pi square by 6. That's cool. Now if you let's say want to find s with 3, you get zeta of 4 as Bernoulli with a subscript 4, 2 to the power 3, pi to the power 4 by sine of 3 pi over 2, gamma of 4, and then 3 plus 1, 4. Now Bernoulli subscript 4 is negative 1 over 30, 2 to the power 3 is 8, pi to the power 4 by sine 3 pi over 2 is negative 1, gamma of 4 is 3 factorial, which is 6 times 4. Negative signs cancels out, and then 4 ones are 4, 4 twos are 8, 2 ones are 2, 2 threes are 6, so it's pi to the power 4 by 90. So we're getting all the values that we like wanted, right? And like now you might want to proceed, and then let's find zeta of 3. Let's substitute s equals to 2, right? What happens? So zeta of 3 will then be a Bernoulli subscript 3, 2 to the power 3, pi to the power, 2 to the power 2, I'm sorry. Bernoulli subscript 3, 2 to the power 2, pi to the power 3 by sine of, this is now just pi, gamma of 3 times 3, right? Over here it seems like it will be some expression in terms of pi cube, right? But the thing over here is the sine pi is 0, and also b subscript 3 is 0. So this is actually 0 by 0, which is indeterminate form, right? Which is indeterminate form. And that's why when if you want to use, let's say, L'Hopital's rule, you now need to maybe take derivative, right? So now the problem becomes like this. Like, I mean, okay, so now the what problems become is now you actually want to find limit instead of the actual value. So what you do is you want to find limit, and then this s goes to 2 of Bernoulli s plus 1, and then 2 to the power s, pi to the power s plus 1 divided by sine pi s by 2, gamma 1 plus s plus 1, right? And now, like, if you want to use, let's say, L'Hopital's rule, because it's in 0 by 0 form, you need to take derivative of numerator and denominator, right? And to do that, again, if you want to take the derivative of this Bernoulli function, like we can actually see Bernoulli thing as like, even though like Bernoulli values seem to be discrete, you can actually just analytically extend it and make it as a function, right? And again, we do that using zeta function. That's the problem over here. Now, like the analytic expansion of Bernoulli function, like this is actually equals to uh, negative s zeta of 1 minus s, right? So now if you want to take the derivative of the denominator, like by having b sub s plus 1 as as minus s zeta 1 minus s, and then take derivative, you will have some expression in terms of zeta function, right? And then again, you will actually need zeta of 3 to find zeta of 3, and like that's gonna be the problem. Like if we let's say had any other like expression, any other analytic expression, then maybe we could have taken derivative of numerator and denominator, and then we would be able to substitute the value and then find zeta of 3, right? So that's what my opinion is about. Like, yeah, if we had, let's say, any other like analytical expansion, then we could take derivative of both numerator and denominator and then actually substitute as equals to 2, and then we'll be able to find zeta of 3. So that's what I think, right? And then, yeah, so I don't really know a lot more than this. Yeah, okay, guys. So yeah. Okay, so I think if you could do that, if we can do as I say earlier, maybe you will be able to find the top 3. So I leave the rest of the thing to you guys, right? And yeah, do try to try, and then if you're able to find the top 3, you will be a great mathematician, and then yeah, the world will praise you. Okay, just before we end the video, I'm gonna actually show you some really good application of the formula we just found in this video, this formula, and then we will end the video. Okay, so we have this formula, right? I guess you guys know, or like general formula for finding zeta of even numbers, right? Zeta of 2n is actually -1 to the power n plus 1, 2 pi to the power 2n Bernoulli subscript 2n by 2 times 2n factorial, right? So let's just like prove this formula using the result that we already have, and then we'll in this video. So if I substitute, let's say, as 2n minus 1 over here, I will have zeta of 2n as Bernoulli subscript 2n 2 to the power 2n minus 1 pi to the power 2n by sine of, if I substitute 2n minus 1, I will have n pi minus pi over 2, and then gamma 2n, and then 2n, right? Yeah, exactly. And now, what I'm gonna do? So what I'm gonna do now is, okay, sine of n pi minus something is just sine of that thing, right? Or is that? Okay, wait. Okay, I substitute 2n minus 1 over here, so this becomes, no, okay, wait. There's n pi, not just pi. So if there's n pi, if n was 1, this should have been positive 1. This should have been just sine pi over 2. If n is 2, there's negative things. Okay, so the pattern over here is 2 to the power 2n. Okay, I'm also gonna take that 2 down for some reason, which might be evident later on, right? Okay, and now this becomes -1 to the power n plus 1 sine pi over 2. Okay, and we know that sine pi over 2 is just 1, right? And I can just negative sign, it doesn't matter if it's in denominator or numerator. So this is gonna be -1 to the power n plus 1, and then 2 pi to the power, okay, so since 2 and pi have same power, so 2 pi to the power 2n Bernoulli subscript 2n divided by sine pi over 2 is just 1, so 2 times, and that's 2n factorial. So we actually we didn't really prove, because we already using a sophisticated formula to get this. There's actually an easier proof for this. But yeah, I just wanted to show you that this can actually be obtained from this expression as well. Even from the reflection formula and using that analytical expansion of Bernoulli, we can actually obtain this formula as well. So I just wanted to show you this, and yeah, definitely I think this is helpful to find zeta values for even numbers. I definitely hope you enjoyed the video, and I definitely believe that you are now a bit more curious than you were, and you're gonna do some maths today. That's it, guys, and if you are gonna do it, my goal is fulfilled. So I look forward to seeing you in the upcoming video. Enjoy, keep doing maths.